And welcome to Week 11, Part 2 of EGM310, Image Enhancements. In this lesson, we will learn about different ways that we can enhance images. We will also learn about how we can use filters to reduce noise or enhance or bring out certain features like edges. Why do we want to enhance images? In this, I'm not talking about being able to zoom in infinitely on an image with increasing clarity, because that doesn't actually exist. By enhancement, we normally mean increasing contrast or improving the distribution of color values within the image. Sometimes we do this to improve the appearance of the image in order to aid in visual interpretation, other analysis, or for aesthetic reasons. We might want to make an image look nice for a publication or for some presentation. Image enhancement can be done in a number of different ways, but there are three broad classes that we will touch on in this lesson. The first is contrast stretching, the second is histogram manipulation, and the last one will be filtering. Let's start with a low contrast image. Overall, this image is extremely dark. You might be able to pick out some features, such as the coastline. You might be able to see that this image shows Port Rush and Port Stewart, but it's hard to get much information out of this image. Doing any sort of mapping or visual interpretation would be extremely difficult. Part of why this is so is because most of the image is very low intensity. I've included a histogram of the pixel values in the image to help illustrate this. In the histogram, the normalized intensity, that is how bright the pixel appears, goes along the x-axis, and the frequency, or how often a particular value appears, goes along the y-axis. So this histogram shows a large peak of values around 0.1, then another peak just above that, and very few pixels with values above 0.2. So most of these pixels have low intensity, and the image appears quite dark. Most of the image is squished into this range between 10% and 20% of the total possible range of values, so we would also say that the dynamic range of this image is quite small. It doesn't make use of the whole range of possible values. The image thus has a very low contrast. The difference between the brightest and the darkest areas is very small. One way that we can improve the appearance is by using something called a linear contrast stretch. By contrast stretch, I mean that we are taking the values in the image and stretching them so that they fill out more of the range of possible values. By linear, I mean that by doing this, the transformation that we use follows that of a line. We multiply by a slope or a scale and optionally add some constant value in order to calculate the values in the new contrasted image. Most GIS software have some way of applying a contrast stretch to an image. In ArcMap, you can find it in the Symbology tab within the Image Properties window. To calculate the scale here, I've used the second percentile for the low end. This is the value where 2% of the pixels in the image are darker than that value. At the high end, I've used the 98th percentile, the value where only 2% of the pixels in the image are brighter than that value. This is not the only way to determine the slope, though. We could choose the maximum and minimum values in the image, or the maximum and minimum possible values for the type of the image that it is. In other words, if it's an 8-bit image, we could choose 255 and 0. If it's a 16-bit image, we could choose 65,335 and 0, and so on. Outlier values can throw off the scaling, though, which we can see here in the second image. This image, labeled min-max, shows that we've stretched the histogram somewhat. It now fills about 0 to 25% of the intensity range, but we don't have many values above 25% or so. This is because there's a small number of abnormally bright pixels in the image. You can see scattered throughout. These are outliers. They don't fit within the range of most of the pixels in the image. To help counteract this, we could take a percentile, for example, using the bottom 2% and the top 2% of values. We could also use the mean pixel value plus or minus a multiple of the standard deviation of pixel values, as shown in the far right here. This doesn't always work if the pixel values in the image aren't normally distributed. You can see that the values in our image are bimodal, and so we have a bit of a lopsided distribution. This type of transformation, linear contrast stretching, can be great because it doesn't distort the image. We're just rescaling it. But it also could mean that we wash out or the brightest or darkest pixels. As you can see here, the beaches look extremely bright and much wider than we might normally think that they are. Another type of contrast stretching that won't wash out the brightest or darkest pixels is what's known as a gamma adjustment or gamma correction. In this type of stretch, the pixel values are raised to some power gamma. If gamma is greater than 1, this has the effect of shifting the histogram to the left, darkening the image. If gamma is less than 1, as shown here, this has the effect of shifting the histogram to the right, brightening the image. In the example here, I've first done a min-max stretch on the original low contrast image. You can see the result of that stretch in the bottom left here. Then I applied a gamma adjustment of 1/2, which shifted the histogram closer to the middle of the range. The image appears brighter. We can see much more detail in some of the darker pictures on the water that we couldn't see with just the contrast stretch. It also allows us to see more contrast without saturating the brightest values. Unlike with the 2 and 98% contrast stretch, the beaches here aren't completely washed out. We can see a lot more brightness variation within it. Sometimes we want to be able to better see local, small-scale variations in an image. To do this, we can use a technique called histogram equalization. In the plot at the upper left here, you can see the histogram of the original image, as well as the equalized histogram. With this, we've stretched out or completely flattened or equalized the histogram so that the values are flat. We don't have pronounced peaks around a given intensity value. This has worked particularly well in the darker parts of the image. You can really see the variations in intensity over the water here, and the differences between a lot of the different agricultural fields are also quite enhanced. Brighter fields have become much brighter, while darker fields have stayed the same or even gotten a bit darker. This can have the effect of decreasing contrast in areas, though. The brighter areas, such as the beaches around Port Rush or Port Stewart, have sort of washed out in this image. We can also amplify noisier parts of an image while decreasing the signal, which makes some things harder to pick out. To help counteract this, we could use a modified technique, such as a local or adaptive histogram equalization, which does the same transformation but over smaller sections of the image. Another variation, called the contrast-limited adaptive histogram equalization, limits the amount of contrast in each of the subregions of the image in order to prevent noise from being amplified too much. Filters are a technique that can either help enhance or smooth image data. They can highlight certain features in an image, or they can be used to suppress features. We use them for things like edge detection, sharpening images, reducing noise. The way that a filter normally works is by doing what's called a convolution, or convolving a kernel by moving it around the image to calculate new values. For each pixel in the input image, we can then calculate the value in the output image using the values that fall within the window or kernel. To see how this works, I have a short example here showing a 3x3 mean filter. That is, we're going to take a window of 3 pixels by 3 pixels and calculate the mean of the values from our image, the value that goes into the output image. So, we start with our image here. Our kernel looks like this. It is an array of numbers called weights. As we move the window around our image, each of the pixels within our window gets multiplied by its corresponding weight, and then it gets added together. For a 3x3 mean filter, the weights are all the same, and they're equal to 1/9. The 9 comes from the fact that we have 9 pixels in the kernel, and we want them all to have the same weight. Here we have our window, which is centered on the blue pixel here. If we then multiply each of the values in the window by 1 over 9 and add them together, we get 16 back out. So this goes into our output image here. And we can keep going to get all of the values in the new image. You might notice that the edges, where we can't get a full window, aren't filled in. Normally we need to specify what to do here. You'll need to check the particular software package to see how it handles these edge cases. One common type of filter is what is known as a low pass or smoothing filter. One example of this is the mean filter that we showed on the previous slide. The term low pass comes from the fact that sharp features or high frequency changes are filtered out, and only the low frequency changes are left. You might also hear this referred to as a blur filter because the end result is that the image appears blurry, as you can see here. One of the most common implementations of this is by using something called a Gaussian kernel. A Gaussian kernel takes the shape of a two-dimensional bell curve. If we look at a 3x3 example here, we see that the largest weight is in the middle of the kernel with a drop-off as we move away from the center. Each of the weights is multiplied by 1 over 16 so that the end result is still an average of the pixels that fall within the window. We can have other variations on this as well. If we want to increase the weight on the center, we might use a 2 sigma or 2 standard deviation version rather than the 1 sigma or 1 standard deviation version, which is shown here. On the left-hand side of this slide, I have an example of a satellite image that has a significant amount of noise in it due to some errors in transmission between the satellite and the ground station. As a result, a number of pixels appear darker or brighter than their neighbors, resulting in a very noisy pattern. You can especially see this with the line running down the edge of the image here. By applying a small median filter, we can smooth out and remove a lot of this noise. It's not perfect, but it does help reduce the impact of some of the noisier parts of the image. This does have the effect of removing some of the detail of the image, some of which is actual real variation. By using some of these tools, we do have to decide which of these things are more important, removing the noise or preserving as much of the detail of the image as possible. To remove the low frequency variation in an image, essentially the color of the image, and just look at the high frequency variations, we can use what is called a high pass or sharpening filter. The way that we calculate this is by subtracting the low pass filtered or blurred image from the original image, which leaves only the high frequency variation. This has the effect of bringing out the sharper edges of the scene. The beaches here really stand out, for example. The color differences between different surfaces are gone. The water here looks essentially the same color as most of the other parts of the image. It's all a fairly even gray tone. This kind of filter can be useful for automatically identifying objects in between two images where the illumination changes dramatically. The shapes and the patterns are preserved and will look fairly similar, even if the color or brightness level changes by a lot. A more extreme application of this kind of filter is something called an edge filter. The purpose of these kinds of filters is, as you might have thought, to find sharp boundaries or edges in an image. Two examples are shown here. Something called a Sobel filter on the left and a Pruitt filter on the right. These types of edge filters work by approximating the first derivative or gradient of the image in either the horizontal or X or vertical or Y directions. If you think back to trigonometry, we can calculate the magnitude of the gradient by adding the square of the x component to the square of the y component and taking the square root. The result of that is shown in the two images here. Anywhere that the filtered image is bright, we have a sharp, well-defined edge in the original image. Anywhere that it's dark, we don't have a very well-defined edge. In a high-resolution image, you might be able to use this to help to help pick out individual buildings or roads or other human-created features, or to find boundaries between different land cover types, not just visually or digitizing by hand, but by also using the computer to do it automatically. In this lesson, we have learned about how we can use enhancements to help us visually interpret images and reduce noise in images. We learned about how we can use contrast stretching, a type of enhancement that increases contrast in images, to help us see more detail and use more of the range of possible values. We also learned about filtering, which we can use to reduce or enhance small-scale variation in images. We also saw some examples where we can use this technique to find the edges of objects in an image. Once again, you can read more about the concepts we've covered in this lesson in the textbooks, Chapter 7 of Lillesand, Kiefer, and Chipman, and Chapter 4 of Campbell and Wynne. I've added links to 3 different videos below. The first 2 talk about some more of the mathematics and computer science behind image filters, while the third shows how you can apply contrast stretches in ArcGIS. That's all for this lesson. I hope you found it interesting, and if you have any questions, please don't hesitate to email me or post in the discussion forum on Blackboard. Bye!